I welcome you all to this evening's RINA London branch presentation. I'm Keith Lee, the president of the branch. Today we have a presentation that's going to be given to us by Dr. Larry Ferreiro, who's a historian and professor from George Mason University in the good old US of A. He's going to give us a presentation this evening entitled, "Why do ships cost far less to develop than aircraft? An in-depth analysis." Larry, as I already mentioned, is a naval architect and historian. He's the 2017 Pulitzer finalist for history for his book, Brother at Arms, An American Independence and the Men of France and Spain Who Saved It. He has received numerous awards for his other works, which include Ships and Science, The Birth of Naval Architecture in the Scientific Revolution from 1600 to 1800, and also Bridging the Seas, The Rise of Naval Architecture in the Industrial Age from 1800 to the year 2000. Larry received his BA in Naval Architecture and Marine Engineering from the University of Michigan in 1980, his MSc in Naval Architecture from the University College London, RCNC program in 1986, and he also was awarded his PhD in the History of Science, Technology and Engineering from Imperial College London in 2004. He teaches history and engineering at George Mason University in Virginia, also at Georgetown University in Washington, D.C., and the Stevens Institute of Technology in New Jersey. He has served for over 40 years in the US Navy, the US Coast Guard, and Department of Defense, and was an exchange engineer in the French Navy. So, as always, Larry, we look forward to your presentation and having such an illustrious speaker. So I'll now hand over to you for your presentation.
Thank you very much, Keith. Two things. First, I am still getting over a chest cold, so I will try not to cough on camera. You won't get it, obviously, but if I have to cough, I will be trying to toggle the microphone. The second, as you can see, this research was actually done under the auspices of my day job, which is at the Defense Acquisition University. I'm Director of Research. Next slide. So I have to present the usual disclaimer. The opinions expressed here don't reflect anybody else's views except mine, even though they were done under the auspices of DAU. These are my findings alone. However, the conclusions that I came to are of interest to the wider naval architecture and engineering and mechanical engineering, marine engineering audience, which is why I'm very happy that RINA has allowed me to present. Next slide. So the itch that I was trying to scratch was started with a report done by RAND, which is an American think tank some years ago, which I participated in this particular study. And RAND was asking the question, are ships different? And the spoiler alert is, yes, they are. The conclusion that they came to, among many others, the one that I wanted to dive deeper on was ships don't follow the usual systems engineering process. They aren't prototyped, and prototyping means something very specific. These are units designated solely for test, and normally the word prototype refers to something that is production equivalent, so something that might serve as a model for what eventually will be fielded, and that is not something that then goes on to serve in the front line. And that's a very different process for ships than almost anything else that's created under not just anybody's acquisition system, be it the American Navy, the British Navy, the Japanese Navy, but also it's different than almost any other major engineering industry like aerospace or the tank industry or cars. Full-scale production for those kinds of engineered vehicles happens after the prototype has been tested and most of the bugs have been worked out or ironed out. That doesn't happen with ships. And so my question, the thing that I wanted to dive deep on was, what does this mean in terms of R&D costs for ships? Next slide, please. So the first thing that I did was take a top line view using publicly available information on ship and aircraft programs. And I chose ships and aircraft specifically because they represent, in many cases, equivalent amounts in terms of unit cost. So a top line ship might have a comparable unit cost to a top line aircraft. And even though the production numbers can often be quite different, excuse me, in theory, once you've done your R&D, you should be able to produce 5 or 10 or 100 models of the same platform, no matter what it is, because you've done the research development leading to production. So I am specifically here comparing not production costs, but the cost to develop and get ready for production these kinds of platforms. And so you can see I've looked at 4 comparisons. The first one is from the UK, where these are 2 programs that were approximately contemporary, 1980s, the Type 23 frigate and the Typhoon fighter. And the development cost for the Type 23 frigate, you can see, is less than $1 billion, where for the Typhoon fighter, it was $24 billion. So there's a 34 times difference in the development cost, and that's before the ship or the aircraft even began production. So I want to be very clear about what I'm talking about. I'm not talking about total cost, I'm talking about just the cost it takes to get the thing ready to be built. So that 34 times is not 34%, it's 340%. So it's an order, it's an order of magnitude difference. You can see the same for the DDG-51 versus the F-22 fighters. Again, these are contemporaries, begun in the 1980s, fielded in the 1990s, 2000s. There is an order of magnitude difference in the cost to develop the aircraft versus the ship. Ships are much less expensive. This was true, and the bottom left is what I'm going to be going into some detail. So let me save that one. And then I also looked at the passenger, meaning the commercial industry, because passenger ships and passenger planes carry people, so they have to be safe. They have to meet stringent standards. They are built in multiple numbers. In a typical cruise ship purchase, you'll have usually 1 plus options, and very often there can be many different models of the same or very similar passenger ships. Look at the Carnival lines. And I compared that with one of the largest passenger planes, the Airbus A380, which I think never really topped 100. So again, the production numbers, although they're different, are not so radically different that they would make this kind of difference in the R&D cost. This is a 200 times difference in the development cost of a passenger plane, $13 billion, versus about $6 million with an M dollars to develop a cruise ship. That's 2 orders of magnitude, 2,000%, whatever form you want to call it. It's enormous, and any minor variations in some of these costs would have almost no effect on the overall bottom line. It is far, far, far more expensive to develop an aircraft, by 1 to 2 orders of magnitude more expensive than it is to develop a ship, whether you are talking about military ships or commercial ships. So that's the first bottom line. Next slide. I wanted to then find out why that was the case. And to do so, I took a deep dive into these two platforms. Again, somewhat contemporary, 1980s, 1990s, the C-17 cargo lifter aircraft and the TAKE Lewis and Clark ammunition ship. Next slide. And why I did this, there's first the mission of the ship, which was to carry cargo. So these are not ships designed to normally accomplish frontline combat duties. So they don't have weapon systems and combat systems, which tend to, excuse me, to skew the numbers. They were, for all intents and purposes, as basic an airframe and as basic a ship as I could find that, and the bottom bullet is the most important, could find cost numbers through public domain sources. You can imagine, for example, that resting with a W, cost numbers from Boeing or from Carnival, and having them published is probably a bridge too far. So these were all publicly available numbers in enough detail that I could make a side-by-side comparison, which I did. Next slide. And this is the second bottom line. The second bottom line is when you're looking at the development cost, and this is only development cost. Again, this is not production cost. Each one of these platforms, when they've been when they were fully developed and in production, cost between 150 and 250 million dollars each. So the cost of the ship and the cost of the airplane to build, that's the unit cost production, was not terribly different. So I want to be very clear about what I'm saying and the basis for why I'm looking at what I'm looking, because frankly, these numbers are surprising. The bottom line is that the predicted 1991 research development um, deployment and testing cost for the C-17 was estimated to be $4 billion. The actual cost from later data that I was able to find took it up to 6.6 billion. By contrast, the R&D cost for the TAKE, most of which was in the detailed design, was only 150 million M. So on the left side, 6.6 billion with a B, right side, 150 million with an M. And one of the differences is that the actual detailed design cost is broken, is distributed throughout these categories. So it's almost impossible to one-to-one compare this specific cost number with that specific cost number. But there's a few things that leap out at you. Let me go to the next slide. The first and most important thing is that a substantial part of that R&D cost for the C-17 is taken up with, as I've already said, the prototypes. These are one flyable aircraft and two ground craft, which were never used for frontline duty. And that was about $2.3 billion just for those prototypes alone. Then you had the structural development and analysis, which included many full-scale tests, power and electronic systems, full-scale, avionics, cockpit mock-ups, full-scale. Look at the TAKE, and apart from the detailed design, which was, as you can see, about $120 million, spent primarily by the shipyard, there were no full-scale tests or prototypes done at all. There was a small model test done. There was early stage design work. There was system integration. None of the big cost items that you see for the C17 are present with the TAKE. So this leads to the obvious question, why should this be the case? Why should aircraft be so different than ships? Next slide. Now, this has been looked at many times. These conclusions come not just from the RAND report that I've cited, but also by analyses done by the Congressional Research Service and other entities. Broadly speaking, if you look at ship programs, the competition is typically at the design stage. Once the program has been selected, the shipyard then goes and builds the ship. And that's true commercial and that's true military. One thing that you don't see is two shipyards building uh, uh, ship prototypes on speculation, having them tested at sea, and then the owner choosing one. Now, I'm talking about ships, I'm talking about ocean going ships. I'm not talking about boats, I'm not talking about recreational craft. I want to be very clear about what we're discussing here. These are large ocean going complex vessels. When we look at development models, you might see them at the system or subsystem engine. You might see a large scale, full scale model of an engine set that happened, for example, on the American FFG program. There were similar propulsion models done for the Type 45 frigate in the UK. But here's the most important thing. The certifications are generally by written rules. They are not by full scale testing and prototyping. So when the design is done and the ship is built, they are generally looked at according to the military specifications generated by the navies. More today, the naval vessel rules, either by Lloyd's or by Bureau Veritas. If you happen to be a commercial ship, imagine yourself, you're a commercial ship. You're going to be classed by one of the big classification societies, Gramanisher, Lloyd, etc. And so those are all written, they're modeled, they're simulated, but there's no full scale testing. If there's a full scale test, it tends to be, does it meet the requirement to stop in a certain distance, things like that. But when we're talking about aircraft, full scale testing means completely different things. First of all, it's not uncommon in military programs to have two competing concepts built to full scale and then flown off. You don't see that with commercial jets, but you do see it for fighters. Many of the engineering development models are done at full scale, so they're building this so you can walk in. Production prototypes are at full scale, and then the testing and certification is many years and always done at full scale. So one is paper and small models and computer generated models. The other one is you build the actual thing and then you test it to destruction. Next slide, please. So I'll walk you through what it looks like at each stage so you can get a better idea of how this change flows through the design and development phase. And this is taken from a typical large engineering program. Military programs follow these steps. Broadly speaking, the first one, I'm not going to use milestone A, B, and C. Concept development, that's the earliest stages where you're just trying to figure out what you want to build. For ships, they're paper studies, they're computer studies. For aircraft, you do both, plus you do a lot of small scale testing, usually in wind tunnels and other types of testing facilities. So already you're seeing a difference at the concept development stage. Ships are never physically modeled. And if they are, that's a really rare occurrence. Next slide, please. Here's where it gets interesting and where you see the big differences. For ships, technology development means you do the early stage design, preliminary design. You put a 30-foot, 10-meter model in a tank. You check maneuvering, you test horsepower, you might check one or two other things, and then you're done. I'm sorry, I'm going to have to pause here, okay?
Just to tell everybody while Larry has been interrupted, we'll have a Q&A session at the end. So if you want to put your questions into the chat box, I'd appreciate that, so we can coordinate that at the end. So let's hope we get Larry back soon.
Hello, I'm sorry. I'm going to continue. I had to take that call. Okay, where was I? I was talking about, can you still, am I on?
Yes, we can see you
Yes,
and hear you
you're
clearly.
fine, Larry. Just continue.
Okay. So I did see a note saying there were ultimately 250 Airbus A380s built. Still not a huge number. I don't know that they ever recouped their R&D costs, and the R&D cost actually went somewhere north of the number I told you. So in terms of aircraft, this is what we're looking at. Typically, there's full-scale prototypes. F-35 Joint Strike Fighter, they built 9 full-scale prototypes. None of these were ever put into service by the two competing companies. One prototype set was for airframe, the other one was for avionics, the other one was for propulsion, and they got to blow up, or at least shoot up, a couple of these prototypes, which we never get to do with ships. We only get to blow them up after they've been in service. And if you're an engineer, that's what you want to do. So we don't fly them off the way aircraft do. Next slide, please. And then finally, when the ships are put into service or ready to put into service in the aircraft, the way they're accepted is also different. As I've already mentioned, the detailed design and construction is certified through plans and then inspection. American Bureau of Shipping, Lloyd's Register, Germanischer Lloyd do this using essentially visual inspections, other inspections, but they're not tested at full scale compared with aircraft. And for those of you who have not seen the bottom left frame, that's an example of what's called a wing braking test. And that's a certification by Full Scale Testing. What's going on there is this aircraft, I believe it's a 787 with composite wings. The wing is being bent until it ruptures, and that is full scale. And the rupture test is intended to first verify that it will meet the load standards, and second to also help improve the modeling and calculations. So this is a full-scale destructive test, and we never get to do that with ships. Most of us would have to go back about 100 years to examples of where we took an actual ship and broke it in half. This is another example of how ships and aircraft are different. Next slide. So I am saying the same thing. It is that the primary driver is the full-scale testing and prototyping for aircraft versus the rules and standards for ships. So this led me to the next question. Why is this the case? Next slide. The first thing I want to do is bust some myths, because in my discussions with many engineers from both sides of the aisle, the aircraft aisle and the ship aisle, I received many comparable explanations, none of which held water, so to speak. The first one is when things go wrong in the air, you don't have time to bail out, where when things go wrong at sea, you have time. Well, that ain't the case. First of all, most of us who are in the commercial world know about the Estonia, which lost 800 people in 1994. That's compared with the TWA 800. Oh, and by the way, fighter aircraft have ejection seats. More recently, we have the cargo ship El Faro, lost with 30 or 40 crew aboard. So the idea that aircraft are more safety critical goes out the window. Ships have lower production numbers. Again, I've already said the numbers are not that different that they would account for the enormous disparity in R&D costs. So, DDG 51, by the time it's done, might actually have 100 units. So that's in the ballpark of F-22s, and the B-2 bombers only has 20. And then finally, the idea that aircraft are more complex than ships also falls by the wayside. There's no widely accepted metric for complexity. Let me be very clear. The metric that I am using was from RAND, which is a very simplistic and not particularly satisfying how many piece parts does it have metric. And just using that, an Ohio class ballistic missile has twice as many piece parts as a F-16 fighter. So again, the potential reasons for in engineering terms of why it should be so much more expensive to develop aircraft falls by the wayside. Let's go to the next slide. My conclusion, number one, is there aren't any valid reasons. Well, I'm going to start from the bottom. There are reasons why shipbuilding programs could and should have full-scale prototyping, because many of the dangers that we face in the maritime world are sufficient to require some kind of verification and validation at full scale. There aren't any real reasons why aircraft could not use the kind of rules and standards method that ships have. And in fact, that did happen, and I'll get to that in a few slides. So the two types of vehicles really could have comparable verification, validation, and prototyping programs, but they don't. So I keep coming back to the same question, why? And as a historian, I will tell you why. Next slide. Ships came from the civil engineering world. The modern methods of designing and building ships were developed at the same time that the modern methods for design and building of civil structures like bridges and skyscrapers and roads and railroads all came about the same time. And if they look similar, it's because the same people did both. In Britain, Isambard Kingdom Brunel famously built bridges, and he built the Great Britain and the Great Eastern. His contemporary, the structural engineer William Fairbairn, did very much the same. And through the history, you saw this parallel development of civil engineering and naval architecture, which never really fully diverged. And this is an example that I love to give. I went to look at web frames and plating analysis in the ABS steel vessel rules on the right, and on the New York City structural code for bridges on the left. And the basic idea that you're using formula based on things like length and depth and a few other items is remarkably similar. You don't see much in the way of um, uh, uh, primary first principles physics. And to give you the example, we have never seen a prototype building. You build a skyscraper, and the skyscraper is the prototype. You build a bridge, and the bridge is the prototype. Even when something like this happens, nobody goes to build a prototype bridge, test it, and then go build a full-scale bridge. And nobody questions it. That's never been a question. So the civil engineering world uses these this method. So do ships, because we come from the same background. By contrast, next slide. Aircraft grew up in the 20th century world of physics. The people who were most noted for development of aircraft engineering, Prandtl and von Karman, they were engineers, but they had the same education as Einstein. It was grounded right from the beginning in first principles physics, and the money followed. As early as the 1920s, we saw this difference. In the United States, there were two ship model basins, one in Washington, the other one in Michigan. The experimental model basin under David Taylor had in then-year dollars $100,000, and NACA, the National Advisory Committee on Aeronautics, which was the predecessor to NASA, already in 1920 had 10 times the funding for R&D. The X programs are another example. In the 1960s in the United States, you had something called the second offset strategy. This was a way of countering the Soviet numbers of troops and guns and tanks, not by trying to defeat them tank for tank and troop for troop, but by outthinking them and pouring huge amounts of money into the technologies. I know in one of the previous discussions I was in with all of you, there was a question about when computer-aided modeling and computational fluid dynamics was developed. That was always developed by the aerospace industry because that's what money was being thrown into. It was all about high tech. It was all about missiles. It was all about guidance systems. Nothing like it was ever pumped into ships. So the money always followed the aircraft. And even today, if you look at the US budget, aircraft account for 3 times in both design, construction, and maintenance and operations, 3 times the amount that's spent across the DoD than for ships. So the money has always followed aircraft, and the R&D and the testing and prototyping and validating follows the same pattern. Next slide. Now, as I said, I just want to be certain you understand that there isn't a valid reason why we could not do what ships do. In the 1930s, ABS, Lloyd's Register, and Bureau Veritas all set up aircraft divisions to do the same kind of class system that was used on ships. And it was successful for a while until governments took over airworthiness, and then that stopped. And they went back to this very physics-based process. Next slide. So my conclusions. Number one, repeating, it is much more expensive to develop an aircraft. And the rationale is not because the platform is different, but because aircraft are the product of 20th century first principles physics-based engineering, and ships are the product of 19th century rules of thumb engineering, and it hasn't changed even here in the 21st century. So my next conclusion, next slide, is that we should not accept this fact lying down. As I've said, there are many reasons why ships should and could and should look more towards systems engineering and full-scale prototyping as a way of improving the product. To give one example, the Estonia, which which had an accident where the bow visor was found to be faulty. Even after that, there was no systematic effort to define the wave loading of why the bow visor failed. There was no effort to make full-scale tests. All of the testing was done by scale models, empirical methods. There are real and cost beneficial reasons why full-scale testing and full-scale prototyping could result in overall savings in lives, property, availability. You know, in the Navy, for example, we've had several collisions of destroyers with cargo ships. None of those collisions needed to have been fatal. There are already structural systems available in the commercial world that can protect a vessel from being holed, meaning having a hole punched into its side because of a bulbous bow. Those have never been systematically explored by any Navy. So there's no reason to discount using full-scale prototyping in building, verifying, and validating ships. And that, next slide, is my presentation. And I'd like to open the floor to questions.
Okay, thank you very much, Larry, for yet another very informative presentation, presented in your usual excellent manner. I'm sure everybody enjoyed it. I did ask that people put questions into the chat line and we'll go through them. So you did see the one there from Jonathan Morley, which was a comment about the number of Airbus A380s. Well, we do have Peter Noble online this evening from Houston, Texas. Welcome, Peter. Nice to have you aboard. He's got a question and a comment. The question regards slide 7, which showed a very high program management cost for aircraft over ships. And he asked the question, why? And his comment was, class rules only cover structure and systems acceptance, not mission performance requirements. So if you can just go to your slide 7.
Can you go to slide 7, Jaime?
And he's asking the question, the very high
PM cost, management cost. Percentage, they are typically percentage of the overall R&D costs. It costs more to manage a $6 billion program than it costs to manage a, well, once you take away the detailed design, you know, a $20 million program. So that explains the PM costs. As far as rules go, here we're talking about things like airworthiness certificates. And airworthiness is a whole series of tests which are done at you know, a combination of full scale plus modeling plus extensive series of flight tests. And Peter, I'm not quite sure I fully understand what you mean by mission performance requirements. Especially for something like the TAKE. So could you elaborate so that maybe we can compare apples, as it were, with apples?
If we can put unmute Peter, maybe you can ask the question directly, Jaime.
Hello, can you hear me?
Yep, fine.
Yes, I can.
Okay.
Hi, Peter. How are you?
Hi, good to see you all, and another great presentation. Yeah, what I was talking about, it was really that the class, and I was familiar from when I worked at ABS about the aircraft registration, but these were about the components and systems. But as a naval architect who designs for a ship owner, the ship owner wants to meet the rules, but he wants the ship to do something. He wants it to go at a certain speed, you know, have a certain seaworthiness capabilities, carry a certain amount of cargo, have a specific fuel consumption. And generally the class rules don't cover those kind of things. So
Yes,
And I
that's true.
don't know, they are covered, of course, because that's on ship trials and things, but they're generally not under class. They're
Yes.
between the owner and the shipbuilder. I just wondered how that was replicated, or was it in, if I buy a passenger aircraft and I want to be able to have this specific fuel consumption, that kind of stuff. That's really not part of the airworthiness certificate, but it clearly
No.
is part of delivering the aircraft that the client wants. So that was
That's
it.
correct. And probably in this detailed cost, you're probably seeing, you're probably not seeing things that were governmental. For example, there are C17 had many load tests where the capability of embarking, trying to remember whether they had to embark M1 tanks or just the M2 Bradleys, and there were fit tests. Many of those things were done by in this case military and civilian personnel,
Yeah.
where the costs really weren't tallied up. So you're right. There's things that aren't covered, but again, what I'm aiming at is this 2 to 3 order of magnitude difference in development cost, which no matter which way, regardless of which way it's sliced, is just an astonishing
No,
disparity.
I completely agree with you, and I go one step further when I compare commercial ship construction with military ship construction. And another semi-political question: I was rereading President Eisenhower's farewell speech, where he's the first time, I think, the military-industrial complex was brought up. Is that a component in the price difference?
No, because, and that's why I brought up the passenger, the cruise ship
Right.
versus the passenger plane. I want to be certain I was not looking just at government versus industry.
Okay. Hey, thank you.
Okay. Oh, you're welcome.
I'll
Okay.
mute myself again.
Next questions.
Yeah, thank you very much, Peter, for your question. Alan Kroll asked a question: do you consider the USN Littoral class ship types Freedom and Independence a success? Were the two types in competition with each other?
First of all, Alan, yeah, I am. You opened up that trap with the punji sticks at the bottom to fall into without putting anything above it, to disguise it, leaves and sticks. My walking into that trap of commenting whether the LCS is a success or not is not one I'm going to jump into. I was actually in the program office. I was there before the beginning. I had many comments prior to it, which I would be happy to talk about offline. I will tell you that the original idea, after some development, was to build 2 prototype, and this was interesting, trimaran ships. By the way, both classes were based on commercial high-speed ferries. So let's be very clear what they were trying to do. They were trying to take a commercial high-speed ferry and make it into a warship. So the idea was they would develop 2 prototypes of each, test them, and then figure out what they wanted to build. And then the need to get more ships into the water ran over that program and made them into, instead of prototypes, made them into actual deployed assets. And all of the teething problems that happened would have been things that would normally be caught in a prototype stage. But like most ships, first of class, they came out in sea trials and operational experience. And almost every ship program manager gnashes her or his teeth when the first of class goes out, because that's where all the problems show up. By contrast, aircraft programs, although they do have problems, they've typically ironed out most of the big problems in the prototyping stage. So Keith, I didn't answer your question because, as I said, there's no way I was going to jump into that particular hole. but I do hope I gave a little bit of context.
Okay.
Okay.
Thanks. That was actually Alan's question. I won't be so pertinent.
Oh,
as
Alan,
well.
not Keith. Sorry.
Yeah. Although I did read it out. Louis, thanks you for your presentation, as indeed we all do. He asks, can the weight reduction and the required low structural safety margins lead the type of tests in place for aviation?
The need to reduce weight is something I looked at. It has some effect, certainly, but it was possible, and it did happen in the 1930s, where lower weight aircraft were built according to sort of rules of thumb that were being used at the time. And they, as far as I can tell, did not suffer any performance. Now, it's a little hard to project what would happen today, but the one thing that you probably already know is that aircraft and ships live in two different environments. Making a ship bigger and heavier actually often saves money, especially if you're talking about building it with more interior space and interior margin and heavier structure that doesn't need to be as finely tuned. You can often get away with making it heavier and having it cost less because the workmanship and the maintenance costs go down. But every pound that you have to lift into the air for an aircraft is costing you in terms of fuel and cost in terms of engines. So displacement is free, but putting something up in the air is not. So they really live in very different environments. But again, and I want to be clear, that by itself doesn't seem to account for the difference, because again, to be clear, that was being done in the 1930s. It was abandoned, but it was successful.